Hi class. In this video here, we're going to talk about section 2.2, which talks about numerical patterns in nature. And we're going to be discovering the beauty of what we call the Fibonacci numbers. And it's really cool. All right. So we notice that there's some naturally occurring patterns that work with numbers in nature. And let me show you what I mean by that. So if you look at these pictures here, I've got a pine cone, some flowers, and I've got a pineapple here. Okay, you'll notice that each of these naturally occurring, not things in nature, have these beautiful spirals to them. Okay, and the spirals are made up of like little pieces. Okay, like if you look inside a flower here, you can see right here, beautiful spirals. Okay, and the pineapple has these other spirals like this. Turns out if you count pieces of the spiral, you're going to get something really interesting and cool. All right. So let's look at the spirals on the pineapple and then at the daisy specifically. All right. So if you anchor yourself right here on the pineapple and you count going to the right until you get to the bottom, you'll count 8 pieces. If you do the same thing going the other way, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You can't see it around the other side, but you would get 12 and then 13. So going to the right, you would get 8, and then going down to the left, you would get 13. So that's pretty cool. Okay, just 2 numbers right there. That'll happen. I encourage you when you go to a grocery store, count that on the pineapples. And then if you look inside the flower here, the daisy. Okay, not looking at the petals, but inside here. If you anchor yourself up here and you count going clockwise, the spirals till you get to the bottom here like this, turns out you'll count 21. And if you go that same other one and then you count going counterclockwise till you get down to the center, you would get 34. Just numbers that occur naturally in the real world. So what's interesting, when you look at those 2 numbers, remember what we have, 8 and 13, 21 and 34. Okay? When you compare these numbers, if you put them in order, right, the question is do you notice a pattern? Well, I'll give you the hint, or I'll help us here. Okay, if you take 8 and 13 and you add them together, you get 21. If you take 21 and the number right before it, 21 and 13, and you add them together, you get 34. This is the pattern. The pattern is a number is the sum of the 2 numbers before it. So, for example, if we have this sequence, 1 and 1, if you add 1 and 1, you get 2. 2 and 1, you get 3. 3 and 2, you get 5. 5 and 3, you get 8. 8 and 5, you get 13. 13 and 8, you get 21. And so look, 21 and 13, when you add those together, you get 34. And then if you have 34 plus 21, that gets you 55. So that's the sequence right there. This sequence, if you keep doing this, you can do this forever and ever and ever, and it'll never stop. This sequence right here is called the Fibonacci sequence. And so let me show you the first few numbers of the Fibonacci sequence that we've had. 1 and 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. And it goes on forever. Okay. And if you looked at the numbers, what we had here, 8 and 13, 21 and 34. Look, 8 and 13, 21 and 34. Those are numbers right next to each other. Okay. These are what we call Fibonacci neighbors. So 2 Fibonacci numbers in a row. All right. So we observed that flowers and pineapple all display consecutive pairs of Fibonacci numbers. Okay, these observations point to some natural bond between adjacent Fibonacci numbers. Like there's something in nature that's causing this. In each case, the number of spirals in one direction is not quite twice as great as the number of spirals in the other direction. Perhaps we can find a richer structure and develop a deeper understanding of the Fibonacci numbers by moving from an estimate to a precise value here. So what I want to do is I want to measure the relative size of each Fibonacci number in comparison to the next one. Okay, so we measured the relative size of one number in comparison to another by considering the ratio. That is by dividing one of the numbers into the other. So here is the list of adjacent Fibonacci numbers and when you divide them. So 1 over 1 is 1. Then we're going to go 2 over 1. That's 2. Then look what I'm doing. 3 over 2. It's 1.5. And watch them. 5 over 3 gets you 1.6 repeating. And if you kept doing this, 5 over 8, then 13 over 8, then 21 over 13, then 34 over 21, 55 over 34, and you keep doing it, it looks like it's converging. Like if you were to keep doing this, like 144 divided by 89 and so on, and keep doing this for all the Fibonacci numbers, okay, with these Fibonacci neighbors, it would converge. It looks like it's converging to some number like 1.6 something. This number here, okay, all right, so notice how the ratio of Fibonacci neighbors converge to a number. This number is called the golden ratio. And I just want to note that the textbook goes deeper into deriving this value. It's really, as part of your assignment, it's worth reading. You'll see how it's derived. And the golden ratio is this Greek letter here. Okay, it's denoted, this is the Greek letter phi. And it converges to, so all these numbers converge that look like they're going to 1 plus the square root of 5 over 2. Whatever this is, it's 1.6 something. This number, the number phi, is called the golden ratio. All right. And besides its connections to nature's spirals, it captures the proportion of some especially pleasing shapes in art, architecture, and geometry. So kind of just to foreshadow what's to come when we're going to revisit this golden ratio when we get into the geometry chapter 4. And what's interesting here is here's a question. And I know this is a subjective question. So like this is a research question that's been asked to people. And it says, what are the proportions of the most attractive rectangle? So if you were to provide these pictures to people, and again, it's totally subjective, okay? And you say, what's the most attractive rectangle? All right. It turns out the majority of people, they would select this rectangle right here. Like when you think of a rectangle in your mind, the rectangle you're most likely going to think about is this one right here. Out of all these 4 rectangles, it's this one. And the reason is this rectangle here, its shape, the proportions, this long side here is like, I don't know, say, let's just pretend and say it's 5 inches. And this short one here is 3 inches. So the ratio is 5:3 right here, which is the closest ratio to the golden ratio. And that's what I mean by it's most pleasing. We see it in nature. We see it in art. We see it in geometry. It's what is pleasing to us. And this is an important concept. And again, we will talk about it when we get to to chapter 4. But I hope this was just a quick, good, short introduction to you for this section of the chapter. As always, you continue to read the rest of the chapter and fill it out. And I'm here for any questions.